Okay. Good morning, everyone. So the chapter name is Virtual Synchronous Generators, Dynamic Performance and Characteristics. So in this presentation, I will not cover all the topics of this chapter, but in the next lecture, I will try to cover almost all the topics. But in this presentation, I will cover the concept of inverter interface distributed generators and microgrids and the principle of the basic virtual synchronous generator control. So here we are discussing about the virtual synchronous generator. So what is virtual synchronous generator machine? First we need to understand. Basically, virtual inertia is established by using short-term energy storage together with a power to noise converter and a proper control mechanism in a system. That is called virtual synchronous generator. So from this definition, it is clearly uh, uh, understood that the virtual synchronous generator control mechanism. For understanding the VSG control mechanism, it is also important to know the important inverter interface distributed generators and their control methods. So this figure depicts the general structure of inverter interface distributed generators. So most of the DGs are equipped with a power tonics converter at the output terminal to convert the generated power to desired voltage and frequency. These converters these converters are usually composed of a DC link and two stages of converter, that is an input side converter and a grid side converter. The input side converter differs according to energy sources and technology. For example, PVs and fuel cells, a boost DC to DC converter is needed because PV panels and fuel cells offer a low DC output. Whereas for wind turbines and gas turbines, an AC-DC rectifier is required. The main task of input side converter is to maintain DC link voltage and to track the MPPT. On the other hand, if we see the grid side converter is always a DC to DC inverter, DC to AC inverter, sorry. And the input side converter may be DC to DC converter and AC to DC converter, but the grid side converter is always a DC to AC inverter. The main task of grid side converter is to regulate generated power, output voltage and frequency, and other power quality issues, and is less dependent on the energy sources. The input side converter depends on our energy source, but the grid side converter is independent of our energy source. And coming to this DC link, in most cases, an energy storage system is connected to the DC link, especially for non-dispatchable inverter interface DGs, such as wind turbines, photovoltaics, to provide an energy buffer for balancing the active power. The DC link storage may be an electrolytic capacitor or electric double layer capacitor, an electric double layer capacitor, or a battery. Which depends upon the how much the if we need more power requirement, then we need the heavy storage system like electrolyte double layer capacity or battery. So now coming to the next section, that is the control methods of grid side converter. Yes. Basically, the control methods of grid side converter can be classified into three basic types. First one is grid forming control, and second one is grid feeding control, and third one is grid supporting control. As the name suggests, grid feeding control, in grid feeding control, actually they auto generate their voltage or reference voltage or frequency, so they forms the grid. But in grid feeding control, it does not set its voltage and frequency, so it needs another voltage support. Means it can't operate independently. It requires one voltage support for the system. And in this grid feeding control, we set the active and reactive power reference, so that accordingly we feed the power to the we feed power to the grid or load. So if we see the grid forming control, in this case, the first if we connect it to the if we connect it to the grid, the first conductor should be closed first forcefully, and then it regulates voltage and frequency. And in this case, as I said, frequency is auto generated. And in grid feeding control, first synchronism must be occurs, so that then MC will be closed. First we have to do synchronism, and then miniature circuit breaker will be closed. And difference frequency in this set in grid feeding control is obtained by the PLL or FLL mechanism. So the grid feeding control can't operate independently. It needs always needs voltage support. And the third one is grid supporting control. Inverter grid supporting control means like inverters that provide other ancillary services like economic dispatch, stability support, power quality enhancement, etc. So both grid forming and grid feeding inverter can be of grid supporting inverter. So if grid forming inverter works as a grid supporting, then it is called as voltage source based grid supporting inverter. That is figure number 2C. And if grid feeding inverter works as grid supporting, then it is called as current source based grid supporting inverter. That is figure number 2D. So in figure 2D, current source based grid supporting control can be considered an upgraded grid feeding control, as its inner loop is in fact a grid feeding control with the added loop control outside that only for providing the power sharing ability. Therefore, like grid feeding control, distributed generators with current source based grid supporting control still need to be connected to a voltage source, as it cannot provide voltage support to the system. So this the figure given in 2D, it needs a voltage support for providing the power to the system. And the voltage source based grid supporting control that is given in figure number 2C can be considered as an upgraded grid forming control, as its inner loop is in fact a grid forming control with the added loop control, provide both power sharing ability and parallel operation ability. So we can differentiate between the figure 2C and figure 2D that here in figure 2C, duplage provide two things: power sharing ability and parallel operation ability. And in the figure 2D, the duplage only provides the parallel operation ability, the power sharing ability, not parallel operation ability. Sorry. This is because in figure 2D it needs voltage support. To operate. That's why here duplage not provide the parallel operation ability. So our topic is virtual synchronous generator, and if we continuation of that differentiation between control methods, virtual synchronous generator is called as an upgraded voltage source based grid supporting control because it provides inertia support additionally. It has all the properties of voltage source based grid supporting control. Additionally, it also provides inertia. So that's why it is called as an upgraded voltage source based grid supporting control. As we know that loop control mimics only the steady state characteristic of synchronous generators, but the virtual synchronous generator controls mimics both steady state and transient characteristics of synchronous generator. So now coming to the principles of virtual synchronous generator control, beginning with the swing equation of a real synchronous generator. This figure shows the dynamic model of a synchronous generator connected to an infinite bus. From the figure, the input power P in is provided by the shaft power Tm. For the shaft power Tm is P in is equal to Tm omega m. Here omega m is the angular frequency of the rotor. Here we have assumed that the number of pairs of poles is 1. Otherwise, it will be like P is equal to P by 2 Tm omega m. For the figure, the relation between output power P out and input power P in can be written as P in minus P out j omega m d omega m by dt plus d omega m minus omega g. This equation number 2 is called as swing equation of a traditional synchronous generator, where omega g is the angular frequency of the bus, j is the angular momentum of turbine generation or moment of system inertia, and d is the damping factor of the damping power introduced by the damp binding, which depends on the power angle delta and the synchronous generator impedance parameters. As we can see in the next slide. Yes. So this is the equation of damping factor. So here V bus is the amplitude of bus voltage, X line is the line reactance, XD dash and XD double dash are the D axis transient and semi transient reactance of the synchronous generator respectively, and XQ dash and XQ double dash are the Q axis transient and semi transient reactance of synchronous generator respectively. TD double dash and TQ double dash are the D axis and Q axis sub transient short circuit time constant of the synchronous generator respectively. As we say, as I said, the equation 2 is known is the swing equation, which describes the inertia feature of traditional synchronous generator, in which both steady state and transient oscillation has been considered. And this here kinetic energy W stored in the rotating mass can be represented as half j omega m square, which is responsible for the transient power balance between the P in and P out. According to swing equation given in equation number 2, if P in greater than if, if P in greater than P out, omega m increases. Omega m increases means kinetic energy increases. This surplus generated power is stored in the rotating mass. And further, if P in less than P out, omega m decreases and kinetic energy decreases. The stored kinetic energy is fed into the power system to compensate transient power storage shortage. And in a steady state, omega m is equal to omega g, and in a steady state, this omega m is equal to omega g, and further d omega m by dt becomes zero. Therefore, P in is equal to P out. This kinetic energy can be further also expressed as the we can say it is proportional to the machine inertia constant h of and the rating of generator g. The inertia constant h of Hello.
Yes, Sahil.
Hello. Am I audible?
Yes, Sahil, you are audible.
Ma'am, up to which slides I have completed?
This after this swing equation, you are explaining the mathematical formula.
Okay, ma'am. I think I lost before that. Okay, I'm continuing from that.
Okay.
Thank you.
Might be some network issues there.
Yes, yes. Here there is power fluctuation, so Wi-Fi got lost.
Okay, okay. Take your time.
So this is the virtual synchronous generator controller scheme for inverter to emulate the swing equation of synchronous generator. So here we can see that there is energy storage between distributed generator and the inverter, and this and which performs this is the kinetic energy stored in the rotating mass is emulated by the energy storage which performs an energy buffer between the input power generated input power generated by the DG and the output power distributed to the AC bus. Normally, the energy storage is a capacitor. An electrolytic double layer capacitor or battery can be optionally used combined with the capacitor for large capacity if required. So here we can see that using voltage and current sensor, we sense the voltage output and current output, and we measure the power, and with the PLL mechanism, we detect the output frequency. And uh, this P out and Q out is fed to the each fed each P out is fed to the and the swing equation block, and Q out is fed to the here compared with the Q reference. And governor model is here is the P omega droop control, and P omega droop control, and here the Q droop and PI together combines the AVR of the AVR of the traditional synchronous generator. And further with addition of P note, B generates the virtual difference voltage for the PWM inverter. And for the swing equation block, we get the virtual rotor angular frequency, and with the integrator, we get the angle for the PWM block, and further it fed back to the inverter. And I will explain all these blocks in detail. So I here the swing equation is a differential equation, an algorithm based on Runge-Kutta. An equation based on Runge-Kutta iterative method is adapted to solve the virtual rotor angular frequency omega m. This is the flow chart of solving swing equation by Runge-Kutta iterative method. The calculated omega m provides the frequency reference of the generator model and the PWM phase reference theta PWM through an integrator. And further, this is the frequency the block frequency detector as shown in the VSG control is responsible for the detection of bus frequency omega g, and here a conventional phase lock loop is used to trace the frequency of output voltage as shown in this figure number 6. So first, the phase voltages are transformed to alpha beta stationary frame by using Clark transformation, and further the alpha beta voltage components are transformed to DQ synchronous rotating frame by using the Park transformation. Here the estimated phase angle theta dash PLL output is used. This one is used. And this works on the concept that the tracking of phase angle of the grid voltage VABC is achieved by the setting the VQ reference is equal to 0. The PI controller serves to reduce the error E to 0. Uh, under this control scheme, for a steady state, the estimated phase angle and the phase angle of actual grid voltage are equalized. So so PI controller reduce the error to 0, and further this omega reference comes here is equal to omega, and this one is the estimated phase angle. Theta dash is the estimated phase angle. And in the block power meter, the output active and reactive power P out and Q out are calculated through equation number 6 and 7. And the low pass filter is used to convert the instantaneous power to average power. Now coming to the next block that is used in the virtual synchronous generator model, that is governor model. Governor model is basically based on the omega P droop controller shown in this figure number 7. Here omega naught is the nominal angular frequency, P naught is the set value of active power, Kp is the omega P droop coefficient, and Td the time constant of governor delay used to emulate the delayed mechanical response of a real governor of a synchronous generator. The range of output limiter for Pin is minus 0.05 to 1.05 per unit. So that we have used here in saturation. Actually, what happens here? Suppose if omega m becomes greater than omega naught, then this droop coefficient tries to reduce the value. So droop coefficient tries to reduce the value by here injecting some constant, so that the set value of active power become decreases. So it directs the control mechanism to give active power less than the before it was giving. So by this proper feedback control mechanism, it further sets the value to set the steady state value to omega naught constant. Further, the block Q drop shown in virtual synchronous generator controller scheme is an VQ droop controller shown in figure number 8. Here E naught is the nominal voltage and Q naught is the set value of reactive power, and KQ is the VQ droop coefficient. And the range of output limiter for Q reference is -1 to 1 per unit, and this is set by the saturation block here. And this figure can be expressed as a mathematically by Q reference is equal to Q naught minus KQ V out minus E naught. So now there are some other virtual synchronous generator controller scheme apart from this control have also been developed in the past. So I am going to describe one by one briefly. So this is the various virtual synchronous generator developed by the several developed under several projects, and various universities are like VSG control developed by VS by NC project, Visma control developed by IP Clausthal University Germany, and VSG control developed by KHI and Synchronous inverter. So this is the brief summary of the virtual synchronous generator developed by the various projects. So I will explain all these in different slides. This is the virtual synchronous generator control developed by VSNYC project. Actually, the VSYN project is under the 6th European Research Framework Program. Is the first research team trying to use virtual inertia control for inverters. As the principle of VSYNC project is to regulate the grid frequency, so their works more focus on the distributed energy storage system rather than distributed generators. So here you can see that they have analysis their model on the distributed energy storage system rather than distributed generators. This control scheme is a current source-based grid supporting control as current loop is applied at the output terminal. A PLL unit is used to detect the frequency of the grid and to provide angle reference for the DQ transformation. The detailed calculation of this current reference based on active and active power reference is shown in figure 10. As we compare the basic virtual synchronous generator control, coefficient K inertia here is analogous to the omega p droop coefficient Kp, and coefficient Kv is analogous to the V omega Vq droop coefficient Vq droop coefficient Kq. Here a unique parameter KSOC is proposed to set the state of charge between parallel distributed energy storage systems. However, the damping factor is not included in this control scheme. So this is the disadvantage of this control scheme. Besides this control scheme is not suitable for islanded operation without a voltage source difference, because this is, as I earlier said, this is the current source based grid supporting control. So it requires other voltage supports to run in parallel. Another virtual synchronous generator developed by that is named as Visma virtual synchronous machine, that is called VISMA control, developed by Institute of Electrical Power Engineering, Clausthal University of Technology, Germany. In these two control methods of Visma are proposed. One is current source based method and the other is voltage source based method, that is shown in figure number 11 and figure number 12. This one is voltage source based Visma control and this one is current source based Visma control. In current source based Visma control, a hysteresis current controller is used to control the output current, whereas the voltage source based Visma control uses the open loop voltage source control. As we can see, in both control, group control laws are not included. So both Visma control methods may not be suitable for parallel operation of inverters. In fact, the voltage source based Visma control can be considered as an upgraded grid feeding control, and the current source based Visma control can be considered as an upgraded grid feeding control. And the next one is the virtual synchronous generator control developed by Kawasaki Heavy Industries. This KHI is also an active research group in the area of virtual synchronous generator control. KHI has developed VSG control for both three-phase and single-phase inverters. For 3-phase inverter, that is shown in this figure number 13, and for single-phase, that is shown in figure number 14. VSG control developed by KHI is for single-phase inverter is an adapted version of based on the double decoupled synchronous reference DDSRF decomposition. Here you can see the Werner model and AVR model create the droop control laws, and a current control loop is presented at the output terminal. Therefore, the VSG control developed by KHI is current source based grid supporting control. Here we can see in both Werner model and AVR model, the input and outputs of droop control laws are opposite to the basic virtual synchronous generator control. That is, inputs are output and reactive power, inputs are active and reactive power, and the outputs are frequency and voltage. In this type of loop control law, first order delay can be used to emulate the inertia. Beside, impedance model is also included in KHI virtual synchronous generator control to emulate the stator impedance of a synchronous generator. And the last one, synchronous inverter. Another well-known inertial inverter control is called synchronous inverter, proposed by Professor QC Zhang for three-phase inverter. This one, actually, the figure is not shown in book, so the basic theory behind synchronous inverter I tell. The principle of synchronous inverter based are very similar to the basic VSG control, except that the damping power introduced by the damp binding is not emulated in the synchronous inverter control. And synchronous is also a voltage source based grid supporting control. So that's all for today lecture, and I will cover the next part of uh, this lecture in the next week. Is there any question?
From my side, there is no question, Kyle.
Okay, thank you.
No questions from my side.
Okay, thank you, ma'am.